Hi all, today I'm talking about chapter 6.3, how to use truth tables to say things about propositions when we don't have assignments of truth values for the statement variables. So before I get to that, let's talk about where we've been in this chapter so far. So far, we've learned how to translate from English language sentences to our symbolic language. We've also learned how to figure out the truth value of propositions when we're given assigned values for the statement variables. Recall that the statement variables are the capital letters, and then that combined with the logical operators and combined with the grouping mechanisms that we have, parentheses, brackets, and braces. Using all of those, we can solve, and the truth tables for the operators, we can solve for the truth value of statements like this. If we knew that A was true and B was true, we could figure out what the truth value of this proposition was. So far, so good. But now, sometimes we'll be asked to comment on what people are saying, and we won't know the truth values of the parts of what they're saying. So what can we say about statements even when we don't know the truth value of the individual smaller parts, the statement variables? To do that, the method we're going to use today is using truth tables. So by the end of today's lesson, what we'll be trying to do is, when given a statement like this, figure out if it's one of these three kinds of statements, whether it's tautologous, meaning always true, whether it's self-contradictory, meaning it's always false, or whether it's contingent, sometimes true, sometimes false, depending on the truth value of the statement variables. So we'll be trying to figure out, given a statement like this, whether it's necessarily true, necessarily false, or whether it's sometimes true or sometimes false, depending on the truth value of A and B. In addition to that, we'll be figuring out how to determine if multiple statements are logically equivalent, contradictory, consistent, or inconsistent. So those are our goals today. Let's try to get there. So over to the right-hand side, I have steps for how to construct a truth table, and we're going to follow those steps with this proposition. So the proposition we're dealing with is tilde A dot open parenthesis B horseshoe A close parenthesis. So we're trying to figure out if this is tautologous, self-contradictory, or contingent. So the first step we need to take towards that end is we need to determine the number of lines in our truth table. So basically what we're going to be doing for this is constructing a truth table similar to the way that we did for our operators over here on the left-hand side. So what are the steps? The first thing we need to do is determine the number of lines in the truth table. So for this, there's an equation. The equation is this: the number of lines in the truth table is equal to 2 to the nth power, where n equals the number of unique variables in the proposition. So, how many unique variables do we have in this proposition? Well, there are 3 variables. How many unique variables are there? So there's A and B, and then we have A again. So we just count from the left-hand side. Here's 1 variable A, here's 2 variables with A and B, and this is A again, but we already counted A once, so we don't count it again. So we have 2 unique variables, so the number of lines would be 2 to the n, where n in this case would be 2. So 2 to the second, or 2 squared. That will be the number of lines in our truth table. So 2 to the second is just 2 times 2. So this truth table will have 4 lines. If we had 3 different variables, so if the second A was a C, Then we'd have 3 variables, then it'd be 2 to the third, which would be 2 times 2 times 2. 2 times 2 is 4, and then times 2 again would be 8. So we'd have 8 lines if we had 3 unique variables. And if we had 4 unique variables, we'd have 16, and so on. All right, so we did the first step up over here to the right. We determined the number of lines in the truth table. The number for this truth table will be 4 lines. So then we construct a truth table. We're on to step 2. Step 2 has multiple parts. So here's the mnemonic device I have for this. What I tell you to do is say a prayer to the God of logic, gods of logic, and ask for guidance in this matter. And that will remind us gods are sometimes associated with crosses, so we make a cross on our page. And we have the bottom of the cross, so beneath the top line, that goes down for the number of lines that we already determined. So if we're doing it on binder paper, we'd put a cross where the top above the line, we'd put a line across on our binder paper. We'd put it'd go up 1 line and it would go down 4 lines. Hopefully that makes sense. It'll end up looking something like this. So you would have here, you'd have above the line, this right here would be the line, and then you'd have 4 lines going down. So 1, 2, 3, 4. So you say a prayer, you draw your cross. You put the variables in the order that they appear in the top left. So here's the top left of our cross. So we're going to put the variables in the order they appear. In our proposition, we first get A. So we're putting A here first. And then we get B. So then we're putting B second. Now, we do that in the top left. In the top right, we put the proposition. So we're going to put tilde A dot, open parenthesis, B horseshoe A. So tilde A dot, open parenthesis, B horseshoe A. All right, so we're well on our way to constructing our truth table. Now, in the key, we're going to fill in a key with all possible combinations of truth values for the variables. So just like over here when we had our truth table for conjunction, we had the variables over here to the left, and we had all the possible truth combinations of P and Q. And then over to the right, we had the way the operator functions with those assignments of truth values. That's the same thing we're doing here. So we're right under here under A and B, we're going to have all possible combinations of truth values for A and B. Now, the mechanical way to produce all truth values is this. We go to the variable furthest to the right, so the B. And underneath B, we're going to alternate true and false. So we have true on the first line, we have false on the second line, we have true again on the third line, and we have false again on the fourth line. Then our procedure will have us move over a variable, so move over to the one to the left, and we'll double the number of true and false in a row. So in the B column, we had 1 in a row, 1 true, then 1 false. In the A column, we're going to double the number in a row, so we'll have 2 trues and 2 falses. So 2 in a row. So true, and then we'll have false and false. If there was a third column, so if there was another variable, if there was one to the left of the A here, then instead of 2 in a row, 2 true, then 2 false, we'd have 4 in a row, 4 true and 4 false, because we're doubling the number in a row from the column that was immediately to the right. So this is a mechanical way of generating all possible combinations of truth and falsity for the variables. We go from when they're both true to when they're both false, with both, the other cases in the middle. All right, so now we just solve. So now instead of one problem, we now have 4 problems, because we're going to solve the truth value of this equation when both A and B are true, when A is true and A is false, when A is false and B is true, and when A and B are both false. And we're going to do that right here. So first, so we're on to step 3 here. We've constructed our truth table in number 2. Now solve for the truth value of the proposition on each line. So the first step we do, just like when we were solving individual for the truth value of the proposition given the assignment of the truth values, we're going to take the same steps. So we're going to write the truth value underneath the statement variables first. So A, we're given in the key over to the left-hand side here, is true. B is true, and A again is true. So now we're going to figure out the truth value of this proposition given this assignment of truth values for the variables. So if A is true, then not A is false, because the tilde flips the truth value. You see that up here. If the statement is true, then tilde that statement is false. And then we're going to move, so we now have handled the tildes that affect single statement variables. That's the only one in the entire problem. Next, we're moving to inside the parentheses. So true, B is true and A is true. So what's the truth value of B horseshoe A? We go down to our conditional truth table over here, and we see when both parts are true, the part before and the part after the horseshoe, then the horseshoe itself is true. So true, horseshoe, true is true. So now we have false and true. The last operator we get to is the main operator, and the main operator of our proposition is this dot. So false and true. When is the dot true? The dot conjunction is only a conjunctive statement. A conjunction is only true when both parts are true. For every other case, it's false. And here we have false dot true. So false dot true, our table tells us, is false. So that's going to be the answer for this line. Now, since I'm on a computer and not super handy with word processing in Word, we're going to just underline and bold this, and that will tell me that that's the truth value underneath for that line, because the truth value underneath the main operator, that's the truth value for the proposition given the assignment of truth values to the variables. So on this line, this statement is false. When A is true and B is true, this statement is false. So now we carry on with this. We go on to the next line. What about when A is true and B is false? Now we're going to solve for the truth value of this proposition given this assignment of truth values. So again, we're going to be building up to the main operator, which is the dot. We're going to start with tildes that affect individual letters. So if A is true, then tilde A is false. Then we'll move inside the parentheses. False, horseshoe, true. False, horseshoe, true. If you look at the truth table for a conditional statement, you see on that line a conditional statement is actually true. Whenever you have a horseshoe is only false when it's true, false, and we don't have that here. This is false, true. So that's going to be true. And then we have false and true is what we're left with. And the dot's only true when both parts are true. So this also is going to be false. Let's line this up a little bit neater here. All right, so I'm going to bold and underline that because that's the truth value for that whole proposition for this assignment of truth values. Now we go down to when A is false and B is true. So we'll fill that in. All right, so when A is false, we start with the tildes that affect individual letters. When A is false, then tilde A is true. And then moving over to the left the right-hand side, now we have true, horseshoe, false. So true, horseshoe, false is the only time when conditional statements are false, so we fill in false there. And now we have true and false. So true and false, the dot is only true when both parts are true. That's not what's going on here. One part is false, so this again will be false. So far we've had every line false. So far if we were going to categorize this statement, we would be tempted to categorize it as self-contradictory, because on every line thus far it's been false. But we still have to go to the last line because there's a possibility it's contingent. So what about when A is false and B is also false? Then what's going to be the truth value of this entire proposition? If A is false, then tilde A is true because the tilde flips. And then over here we have false, horseshoe, false. If we look at the truth table for conditional statements, we see false, horseshoe, false is actually true. So now we're left with true and true. And if we look at the truth value for conjunctions, we see that's the only case when the dot's true. So here we are left with true under the main operator. Now, if I were doing this with pen and paper, I would put a box around. So I've done step 3. I've solved for the truth value of the proposition on each line. Now I'd go to step 4. I'd put a box around the truth value under the main operator. So if I was doing this by hand, I'd draw a box, a long box around the FFFT here, to highlight that that's the truth value for the entire proposition on those lines. And then I'd classify the statement according to these various definitions. So now I have to figure out, given FFFT as my truth values on these lines, is my statement tautologous, meaning it's always true? Certainly not, because I have 3 falses here, so it's not tautologous. Is it self-contradictory? Is it all false? No, it's not all false, because I have a true here on the last line. So the only remaining possibility is its truth value is contingent upon the truth value of the statement variables. So contingent just is another word for depends upon. So the truth value of the proposition is contingent on the truth value of the statement variables. So some in logic always means at least one. So it's sometimes true, sometimes false, meaning there's at least one line that's false. In fact, there are 3, and there's at least one line that's true. There's 1. So the truth value, what can we say about this proposition absent any if we're not given the truth value of the statement variables? We can say, well, this proposition, it might be true. If somebody said this, it might be true, it might be false, depending on the truth value of A and B. And if we were doing it on the test, we would just fill in the bubble for contingent. Good. So that's the procedure we're going to be going through for all of these. Let's go through one more here. Let's say we had A or C dot B horseshoe C. And let's go through the same procedure. If you already think you have it down, what you might want to do is pause the video right now, try it yourself, and then see if I'm doing it the way you did it. Check your work. All right. So we're going to first determine the number of lines in our truth table. So the way we do that is we count up the unique variables from left to right. So we have A is 1, C makes 2, B makes 3, and then we have another C, but we already counted C. So we have 3 unique variables. So when we're determining the number of lines for this proposition, it's going to be 2 to the n, so 2 in this case to the 3rd power. So that will be 2 times 2 times 2. So 2 times 2 is 4, times 2 will be 8. So we'll construct a truth table with 8 lines. We say a prayer, we make our cross. Up in the top left-hand corner, we put the variables in the order that they appear. which I did not do. We got A, C, and then B is the order that they appeared in this proposition. Now we're going to fill in the truth value. Well, we make a cross that goes down 8 lines. Up in the left, the variables in the order that they appear. Up in the right-hand side, we put the proposition. Now, now we need to fill in the truth values. So we'd go to the far right-hand column under the B, and we would alternate truth and falsity. So it would go true, false, true, false, true, false. Then we'd go to the C column, and it would go true, true, false, false. We double the number in a row. So true, true, false, false, true, true, false, false. And then in the A column, we double the number in a row from the column immediately to the right. So on the C column, we'd have 2 in a row. In the A column, we'd have 4 in a row. So that I don't drive myself crazy doing this, and don't waste your time, I'm going to pause it, fill in the truth variables myself, and come back when they're all filled in. All right, so now we have the truth values for this underneath the statement variables for all 8 lines, all 8 possible combinations. In the B column, we did true, false, alternating all the way down. In the C column, we doubled that, true, true, false, false. In the A column, we doubled that again, the number in a row. So 4 trues in a row and then 4 falses. All right, so now we're going to solve for the truth values, the truth value of the proposition on each of these lines. So when all statement variables are true, let's figure out the truth value of this proposition. So A is true and C is true, so A or C, we'll be looking at the disjunction. When they're both true, the wedge is true. And B horseshoe C, so when both parts of a conditional statement are true, then the conditional statement is true. We'll get true there. And then we have true and true. So true and true. If we looked at the conjunction table, when both parts of a dot are true, then the whole thing is true. And we'll bold and underline that. So the statement is true on that line. Now what about when B is false? I'm going to take a shortcut here and tell you that when B is false, we're going to get true on this line as well. The only difference from the previous line is we'll have false, horseshoe, true, and that is true. So we'll get true on both sides of the dot, and we'll get true under the main operator. How about when A is true and C is false? A is true and C is false. B is true and C is false. On this line, true or false. So true or false, so we go to the disjunction. It's true on, the wedge is true on that line of that table, so it's true here. So far this conjunction is looking good. On one side it's true, but we need the other side to be true as well for the conjunction to be true. So we come over here, when B is true and C is false, that's the only time when a conditional statement is false, is when the antecedent is true and the consequent is false. So here we'll have false on this line. And then we have true and false. So what's the truth value of the proposition on this line? It is false. And we're going to bold that and underline it. Now, we can save ourselves a bunch of work. Why? Because what we're looking for in this statement is to figure out if it's tautologous, so if it's always true, if it's self-contradictory, meaning always false, or if it's contingent on the truth value of the statement variables, meaning it's sometimes true or sometimes false. And we've actually already found that it's sometimes true. On these two lines it's true, and on this line it's false. We don't need to do the rest, because regardless of what we get on the rest of the lines, the truth value for this statement is also contingent. So it's great when you find at least one true and at least one false, because then you can stop working. If we were getting a run of trues, we'd have to keep going until we found a false or until we got to the end to determine if it was contingent or tautologous. If we had a run of falses from the beginning, we'd have to keep going to see if it was self-contradictory, meaning all false, or if there would be a true hiding at the bottom of the table. So this is contingent as well. So what have we learned so far? We've learned how to figure out if single statements are tautologous, self-contradictory, or contingent. There's one more piece to this puzzle, and that's to figure out the relationship between two propositions without given an assignment of truth values for either of them. So how do we do that? We're going to construct a truth table, so these steps over here are going to remain there. There's just going to be a little bit of a wrinkle. So two propositions. So let's say we were given K horseshoe L and tilde L horseshoe tilde K. Let's say somebody put these in an argument as premises for an argument. And we were wondering, but we didn't know whether K or L were true. And we were wondering, well, can this argument be a good argument? Or let's say that we just held two beliefs, and the beliefs had the form of K horseshoe L and tilde L horseshoe tilde K. Could these beliefs possibly both be right? Let's see. So how are we going to do? So first, what are we looking for? With two statements, we're looking to see, are they logically equivalent? So are they saying, do they have the same truth value on every line? So when the first one's true, the second one's true. When the first one's false, the second one's false. Or are they contradictory? Do we get different results on every line? So when the first one is true, the other one's false. When the first one's false, the other one's true. That's the question we have to answer first. So are they logically equivalent or contradictory? If the two propositions we're looking at are neither of those, then we have to ask the further question, are the propositions consistent, meaning there's at least one line on which both statements are true, one assignment of truth values, such that both propositions are true, or are they inconsistent, meaning there's no line on which they are both true? So let's do the propositions we have, and we'll come back to this for some examples. So what we're going to do is we're going to put these two statements on the same truth table. Now, what do I mean about the same truth table? We'll have the same order of variables up in the top left and the same assignments of truth values. That's really important. If we put these on separate truth tables, we'd actually have different keys, because in this proposition, K occurs first and L occurs second, so that's the order we followed up here. If we were to put this on a separate truth table, we'd have L occurring first and K occurring second. And if we put this on a second table, then the truth values would be, of the middle two cases, would be flipped around, and there'd be chaos in here. We don't want to do that. So we want to put these on the same truth table. And now we're going to figure out the truth values for these propositions, given these assignments of truth values. So we essentially have 8 problems to solve here. Luckily, this is a simple horseshoe, K horseshoe L. And we have K coming first and L coming second. So what we're going to end up with is a truth table that looks like this, where when they're both true, then K horseshoe L will be true. When it's true horseshoe false, that's the only time when a conditional statement is false. And so when we have a false antecedent, we actually have a true conditional statement. So we'll end up with a truth table that looks like this. I skipped the step of putting the truth values from the key underneath the statement variables, but you can fill that in if you want to. All right, so this is what the truth table looks for this proposition. Let's see what the truth table looks for this proposition. So we again have a horseshoe, but we have tildes in front of the letters. So let's see how that affects it. So when L is true and K is true, then the tildes will flip both of these trues to false. So we'll have false, horseshoe, false, and we look at our truth table for conditional statements. When we have false, horseshoe, false, we actually get true. So on that line, this statement is true. So far it matches up with the other statement. Let's look at what happens when K is true and L is false. So we have L as false and K as true. So when L is false, then the tilde will flip it to true. And when K is true, then the tilde will flip it to false. So we're going to have true, horseshoe, false, and that's the only time when a conditional statement is false. So we'll get false on that line. Note the pattern here. So far we're following what's happening on the other in the other proposition. So what about when K is false and L is true? When L is false, then when L is true, then the tilde is going to flip that to false. And when we have a false antecedent, we know that the conditional statement is true, so we don't really need to worry about the other side much. So this is going to be true on this line. And then we go to the final line. What about when they're both false? When L is false and K is false, then the tildes will flip each of these to true. And then we'll have true, horseshoe, true, so we'll get true for the truth value of the entire proposition. So now we're going to inspect our truth table. If I was doing this on a piece of paper, I'd put a box around the truth values under the main operator of each of these. Since I'm doing it in a word processor and I'm not handy with it, I just bold and underline. So I guess to be consistent here, I would bold and underline these. So then what have I done? I've done steps 1 through 3 over here, and then I'm going to do step 4, put a box around the truth values under the main operator of each statement now, or of each proposition, and then I need to classify the relationship between the statements according to the definitions. So let me go down to my definitions. Are these logically equivalent? That's the first question I ask. Do they have the same truth value on every line? So on this line, they're both true. On this, they're both false. On this, they're both true. On this, they're both true. So, in fact, if I was doing a test on this, I would say these propositions are logically equivalent. I wouldn't even ask any of these other questions. I'd just stop at logical equivalent. All right, so let's say we had a different proposition up here, and I'm not going to fill in what that proposition is. I'm just going to assign some truth values here to see to talk about the difference between logically equivalent, self-contradictory, consistent, and inconsistent. So let's say I had some proposition up here, and I got these truth values. I'm going to change the truth values a little bit. So let's say instead of true on this line we had false, instead of false on this line we had true, and then on this we had false, and on this we had false. Imagine I did the work. I filled in the key, I did the work for this weird proposition, and let's just have it as P, and I got these truth values. Then I'd ask myself, are these logically equivalent? And I'd see, no, the first line shows me that that's not the case. They don't have the same truth value on every line. Are they contradictory, meaning different truth values on every line? Here is true and then false, false and then true, true and then false, true and then false. I do have opposite truth values. So these are contradictory, and I'd stop right here. I have these statements are contradictory. They have different truth values on every line. Now, imagine a different case. Imagine this was true on this line. Now I'd ask, are they logically equivalent? They're the same on this line, but different on this line. So they're not logically equivalent. Are they contradictory? Different truth value on every line? No. They're both true on this line. So they're not contradictory. Then I ask, are they consistent? So is there at least one line on which they're both true? And the answer to that is yes. On line 1, they're both true. So these are not logically equivalent, they're not contradictory, but they are consistent. If somebody said this, and whatever proposition this was, there's a possibility that they could both be true, so they're consistent. Imagine now instead we had this as our two propositions. Are the truth values for these two propositions. Let's go through it again. Are they logically equivalent, the same on every line? Well, they're the same on this line, but now they're different on this line. So they're not logically equivalent. Are they contradictory? No, they're the same on this line. So they're neither logically equivalent nor contradictory. So then we ask, are they consistent? Is there at least one line on which they're both true? Well, on this line, they're both false, so they're not both true. On this line, one's true, one's false, the other's true, so not that line. They're not both true on that line. They're not both true on this line. They're not both true on this line. So these are inconsistent. There's no line on which both statements are true. All right. So what have we done today? Today, we've learned how to use truth tables to figure out if single statements are tautologous, self-contradictory, or contingent, and how to use truth tables to figure out if multiple propositions are logically equivalent, contradictory, consistent, or inconsistent. Good luck with quizzes and homework this week. I'll see you next time.